Hi, everyone. My name is Daniel Wynn, and today's material on thermal challenges in advanced packaging is brought to you by work done in the SCAN lab under the supervision of Aslam Khan, Hima Coder, and Dr. Naveed Asadi. The content of this video will be centered around thermal challenges in advanced packaging, more specifically, heterogeneous integrated packaging, and is outlined by the following topic titles: Thermals in Electronic Packaging Overview, Material Thermal Properties, Thermal Challenges in Heterogeneous Integrated Packaging, Thermal Challenges in Advanced Heterogeneous Integrated Packaging, 2D versus 2.5D versus 3D thermal challenges, miscellaneous thermal challenges, mitigating these thermal challenges, future trends in thermal management, glossary, and then the references. First off, I will be discussing about a general overview of thermals in electronic packaging, specifically advanced electronic packaging. In advanced packaging, it is required to have effective thermal management. Advanced packaging is all about improving capability whilst making packaging smaller. However, smaller electronics tend to generate more heat in tight spaces. And without effective thermal management, this can lead to overheating, material stress, and device capability throttling, which can cause device malfunctions or failures. The figure on the right shows a heat map of integrated circuits and the thermal ranges they can experience from just different placements of the through-silicon vias. Optimal and adequate thermal management can ensure a user's safety, preventing possible burns, fires, and explosions. There are different ways to improve the thermal management in electronic packaging, and the materials used are one of the most important. Some of the most important types of material thermal properties are thermal conductivity, thermal resistance, specific heat capacity, thermal expansion coefficient, and thermal diffusivity. Thermal conductivity is a material's ability to conduct heat. As most recently stated, this is incredibly important for the thermal interface materials to help improve heat transfer in an electronic package. Thermal resistance is a material's ability to resist heat flow. This is important in insulators used in electronic packaging to contain heat in certain areas or protect the components from external heat. Specific heat capacity is the energy needed to raise the unit temperature by 1 degree Celsius. These materials can absorb more heat, protecting components during thermal stress. Thermal expansion coefficient is how much a material expands when heated. Because of this, different materials within electronic packaging are chosen with similar coefficients to prevent thermal expansion mismatches. And finally, thermal diffusivity is how fast a material dissipates heat, which allows heat to spread away from the hot spots quicker. Starting off will be thermal challenges in heterogeneous integrated packaging, more specifically in 2D chips. 2D chips have a power density that creates significant heat during operation. This heat needs to be managed effectively to ensure the chip's performance and longevity. However, there can be a mismatch in heat tolerance between the different materials in the chip, which can complicate this heat management. Efficient heat balance and distribution are essential. Engineers must design systems within the chip that distribute the heat evenly and prevent hotspots, which can damage the semiconductor materials. Another critical factor is heat movement and removal. The goal is to move heat away from the semiconductor die and remove it, typically using heat sinks or cooling systems. Interposer thermal properties also come into play. The interposer material, which could be silicon, glass, or organic materials, can effectively conduct the heat away from the chip. Different materials have different thermal conductivities, which can impact their ability to manage heat. The figures on the right illustrate various packaging configurations and their thermal assessment, showing how different layers and materials in the chip package influence the overall heat flow and thermal resistance. This helps engineers understand how the choice of materials and package structure can affect the chip's ability to handle heat. Moving forward with thermal challenges in heterogeneous integrated packaging is in the context of 2.5D chips. 2.5D chips are a stepping stone between traditional 2D flat integrated circuits and full 3D integrated circuit integrations, and presents specific challenges due to their increased power density. This refers to the amount of power used or dissipated over a given area. And managing this heat and power in larger, high-powered chips is critical for maintaining performance and reliability. Ensuring efficient thermal conduction is also important. The heat generated by the chip must also be spread evenly and dissipated effectively to prevent hotspots that can impair function or lead to failure. At both the package and chip levels, you must see a balance be held. The package, which houses the chip, must support this heat management, often through materials that have good thermal properties and design features that aid in the movement of heat. Advanced packaging technologies use an interposer, often made of materials like silicon glass or organic substances, to facilitate connections between chips and the PCB board. The interposer itself can also contribute to the thermal management challenges, as seen in the figure on the right. In advanced semiconductor packaging, particularly with 3D stacked chips, the thermal management is a critical challenge due to the increased power density, as is seen with the other lower level chips. As more transistors are packed into these compact spaces, the heat generation during operation also increases. These 3D chips have a complex heat conduction path. Unlike 2D chips, where heat dissipates mainly horizontally across the chip, 3D chips require managing heat in the vertical direction as well. Vertical core alignment, where cores are stacked on top of each other, adds complexity to cooling design because heat from all the layers needs to be managed effectively together. To address these issues, the semiconductor industry uses high bandwidth memory, also known as HBM, which can create thermal bottlenecks due to its dense stacking. HBMs are an example of how power density can affect thermal management. The efficiency of heat conduction becomes super important to ensure that the system maintains optimal temperatures for reliable performances. These challenges require innovative cooling solutions and an in-depth understanding of both the package and chip level thermal properties to develop semiconductors that can operate efficiently within safe temperature ranges. With that being said, this brings us on to the next 3D stack chip, which involves liquid cooling. Moving on to thermal challenges in advanced heterogeneous integrated packaging, we move on to the 3D stacked chip. In the 3D stacked chips, due to their architecture, they face an increased power density which traditional heat conduction methods might not effectively manage. These chips are designed with multiple layers of semiconductor materials, also known as front end of the line and back end of the line, FEOL and BEOL respectively. FEOL refers to the initial phases of chip fabrication where the active components of the devices are created, and BEOL involves the latter stages where the interconnections are formed. The complexity of these internal structures with their intricate FEOL and BEOL layers makes thermal management more challenging. The heat needs to be conducted through these multiple layers efficiently to prevent overheating, which can cause the device to fail. To combat this, integrated fluid dynamics design comes into play, utilizing liquid cooling methods embedded within the chip package. This co-design approach assures that both the materials and the cooling systems work together effectively to manage heat by spreading out and away from the chip. Photonics-based packages represent a cutting-edge area in semiconductor technology where light is used for rapid data transfer within chips. These packages are also facing several thermal challenges that need to be addressed. First, due to their nature, photonics-based packages have an increased power density as well. The packaging of optical components with electronic circuits together in a confined space leads to a significant amount of heat being generated. Operating temperature can also be a critical factor. Photonic components need to maintain a certain temperature range to function correctly, and if the temperature is way too high or way too low, the performance of these components can be severely impacted. This leads to dual thermal criteria in such systems. The electronic parts need to be cooled to remove excess heat, while the photonic parts need a stable temperature for optimal performance. Finally, the integration of photonic and electronic components pose significant challenges. This not only involves the physical assembly of the different components, but also ensuring that the thermal management solutions do not interfere with the operation of the photonic components themselves. Hence, that addressing these thermal challenges require innovative materials and cooling solutions. Advanced packaging, such as antenna packages, provide their own unique challenges. These systems integrate antenna components for radio frequency, also known as RF, communication directly into the semiconductor package, leading to specific considerations for heat management. First, the heat generated within the package can interact with RF signals. It's crucial to maintain the integrity of these signals, as heat can affect the signal strength and quality. Thermal expansion material mismatch is another concern. Different materials in the package expand at different rates when heated, which can lead to physical stress and even failure of the package. Thermal shielding is necessary to protect sensitive parts of the package from heat generated by other components, like the antenna or the processing units. Effective shielding ensures that heat does not interfere with the AIP's operation. And lastly, there are a lot of cooling limitations to consider with antenna in packages. The compact nature of AIP systems means that traditional cooling methods such as large heat sinks are not viable. Innovative cooling techniques must be integrated without compromising the size or performance of the package and antenna. The schematics provided on the right shows the layers of the AIP system, including the RDLs, through silicon vias, and positioning of the antenna, emphasizing that the multi-layered and compact nature of this sophisticated system needs to be treated carefully when managing the thermals. Semiconductors must sometimes operate in extreme conditions, and these harsh environments, like those found in aerospace, automotive, and space applications, impose strict requirements on thermal management. The reliabilities of these systems are crucial, so the packaging must be designed to handle significant variations in temperature and other stress factors. For these type of applications, topside cooling solutions are often necessary. Unlike traditional methods where cooling elements are placed below or around the chip, topside solutions focus on removing heat from the surface of the chip that faces away from the substrate. This is especially important in high-power systems where the heat generated at the top of the chip must be managed effectively. Semiconductor packages in these environments also often contain dissimilar heterogeneous components, meaning they're made from different materials with different properties. Creating thermal management solutions for these kind of systems can be complex due to the different ways materials react to heat. Thermomechanical solutions are engineered to address these challenges. They are designed to accommodate for the physical changes that occur due to thermal expansion or contraction, and to ensure that the semiconductor continues to function correctly. The diagrams on the right illustrate the concepts of notional 3D chip architecture with anticipated topology challenges, highlighting the need for TIM, also known as thermal interface materials, can conform to the 3D contours of advanced chip designs. The depicted encapsulated low melt point solder thermal interface system suggests that a method to create a more effective thermal pathway is in the way for complex chip architectures. As technology advances, mobile platforms such as smartphones continue to shrink in size, a process known as miniaturization. However, this miniaturization increases the complexity of electronic packages and presents significant thermal challenges themselves. One major issue is the creation of processor hotspots, areas that generate more heat due to the concentration of electrical activity. The thermal image shown on the right shows the temperature distribution on the surface of a smartphone, indicating areas with varying temperatures. These hotspots need to be carefully managed to avoid overheating those areas, which can affect device performance and longevity. To address these thermal issues, manufacturers use advanced thermal materials and structures like micro heat pipes to dissipate heat effectively. These materials are engineered to conduct heat away from hotspots and spread it over a larger area for it to be more easily dissipated. Dynamic thermal managed systems are also critical. They adjust the device's thermal response based on real-time temperature readings, helping to prevent overheating during intensive tasks such as gaming or video processing. These systems ensure that the device operates within safe temperature ranges, maintaining performance without sacrificing user comfort or the device safety. Switching focus to the role of voltage regulators in thermal
management. Voltage regulators are essential for managing the power within a device's circuitry. They ensure that the components receive a stable voltage despite the fluctuating demands of the device's operation. Advancements in design are also leading to smaller, more efficient regulators, but this evolution comes with challenges. As devices become more powerful, they draw increased current, which can lead to higher power density and more heat generation, also known as ohmic losses. Local decoupling is a technique used to minimize power distribution noise by placing small capacitors close to the device's power pins. This can help with power stability, but can also add complexity to the thermal management of the system. Hotspots are areas where heat is concentrated, where often the voltage regulators are working their hardest. Managing these hotspots are critical in preventing overheating and potential device failure. Cooling imperatives in voltage regulator design are becoming more important as power density increases. Designers must consider how to remove heat efficiently while keeping the device compact and functional. This includes using materials that conduct heat away from the hotspots and designing the physical layout to allow for effective heat dissipation. The figures on the right showcase a system in package with an on-die voltage regulator and a package level DC to DC level shifted voltage regulator. These components are critical for power management within the package, but also is designed with thermal considerations in mind. Moving on to direct comparisons between 2D, 2.5D, and 3D thermal challenges in packaging. In 2D packaging, components are arranged on a single plane, which generally presents the least complex thermal management scenario with lower power density and direct heat dissipation pathways to heat sinks. Hotspots are less frequent, and standard cooling solutions like heat sinks and fans are typically sufficient. As we move to 2.5D packaging, which includes interposer-based components for heterogeneous integration, the thermal challenge increases. The power density is higher than in 2D, but lower than in 3D packaging. Heat dissipation becomes moderately complex because it has to navigate through the interposer to reach the heatsink. There's a higher incidence of hotspots compared to 2D inside 2.5D, becoming more necessary for more advanced cooling solutions and possibly liquid cooling. Effective lateral heat spreading becomes an important part due to increased complexity of the thermal pathways. 3D packaging, which stacks chips vertically, poses the highest thermal challenge due to increased power density from the stacking and the complexity of vertical integration. Heat dissipation in this context is the most complex, with thermal pathways moving throughout multiple dies, leading to frequent and intense hotspots. Cooling systems often require embedded systems which can complicate the design further. Heterogeneous integration, which involves combining different types of components like memory logic into a single package, increases these challenges, particularly in 2.5D and 3D packages. Managing the different thermal characteristics and requirements of these diverse components adds a level of difficulty, requiring innovative thermal interface materials and dynamic thermal management strategies to maintain device performance and reliability. Moving forward to the mitigation innovation of thermal interface materials, also known as TIMs. TIMs enhance heat transfer between components and heat sinks. The balance between conductivity, how well they transfer heat, and compliance, how well they conform to surfaces, is crucial for their effectiveness. Composites are TIMs that combine materials such as metals and carbon with a matrix-like polymer to improve thermal properties. Nanostructured TIMs take this further by incorporating materials with nanoscale dimensions to increase the surface area for heat transfer. These materials can be directional, which means they conduct heat better in one direction than another. This property can also be anisotropic, favoring one direction, or isotropic, equal in all directions. Some TIMs use a phase change to absorb heat. They change from solid to liquid at certain temperatures, which can absorb large amounts of heat. The goal is to create TIMs that are highly conductive and compliant to fill in microscopic gaps for better heat conduction. The figures shown on the right show examples of high-performance TIMs, including a graphene polymer composite, vertically grown nanotubes, and vertically electrodeposited nanowires. representing cutting-edge materials designed to meet these thermal challenges and their criteria. Exploring more into the future trends in mitigation innovations are air-cooled heat sinks. These components are critical in managing high heat flux, which is the rate at which heat is transferred per unit area. Several factors drive their thermal performance, including the efficiency of airflow over the fins, which is sometimes limited by the design and placement within a system. Integrating heat pipes into heat sinks is a design evolution that significantly improves heat transfer capabilities. Heat pipes work by evaporating a liquid at the hot end and condensing it at the cold end, effectively transferring heat away from sensitive components. The form factor, or physical size and shape of the heatsink, also influences its performance. It must fit within the available space while providing enough surface area to dissipate heat effectively. Alternatives to air-cooled heatsinks are also being developed. Liquid cooling systems involve the flow of a coolant in direct contact with hot components. Two-phase immersion cooling submerges components in a thermally conductive liquid that boils and condenses to remove heat. Water-cooled systems uses water's high thermal conductivity to absorb and transfer heat away. Vapor chambers function similarly to heat pipes, using phase change to transfer heat across a flat plane. Each of these alternatives has its own benefits and challenges, and their application depends on specific system requirements and constraints.
Here's the glossary. Here are the references.